All right. Thanks, man. Um, so our goal right now is to learn about tangent lines at a point. So what have we talked about to help us understand tangent lines at a point? So far, what are some terms we've thrown around, or some ideas that we've talked about? Can anybody throw them into the chat or vocalize them?
We talked about how the tangent line will just touch like at one point on the graph.
Yeah. So the tangent line
Like
touches.
kiss the graph.
Yeah. Kisses. And this is a really important idea. Thanks for bringing it up, Summer. It's very important. It kind of creates a problem, but it'll motivate our definition for the derivative when we come up. What's something else we talked about? And it doesn't need to be nearly as important as what Summer shared. Just anything.
You said how it usually it stays on one side.
Yep. That's a good point too, is when you're sketching a tangent line, it's good to remember that it's usually staying on one side. And then I said, except at what I called an inflection point, which we'll talk about later, so you can recognize them. But there's these points that they actually cross. They kiss and they cross at the same time. What's something else that we mentioned last time? These 2 points are important. They're great. They don't need to be as weighty or as deep as those ideas. Anybody? Instantaneous rate of change. Selena put that into the chat window. Absolutely. Very important term. Okay. I'm not going to talk about what it means right now. What's another term or phrase or idea that we mentioned last time?
You mentioned stretching and compressing.
Uh-huh. As kind of what, if a function is a rule that assigns to each input a unique output, you can think of a function as stretching the domain or compressing the domain or folding it or tearing it or something like that. And what tangent lines help us understand is if or how the function is stretching or compressing the domain. Good. What's another idea? Local linearity, absolutely super important. And the local linearity was a way we discovered that there was even a tangent line, right? We zoomed into a graph at a point and we saw it look straight. We estimated the equation of that straight line. And it turned out when we stepped way back out, we zoomed back out, that straight line turned out to be the tangent line. Okay, super important idea. Anything else?
How to calc the slope of a tangent line?
So what I'm going to do is I'm going to say how to estimate, calculate the slope of a tangent line. Yeah, we talked about that too. Right. Anything else? Anybody else want to throw out there? These are all good and important ideas, and you need to understand all of these things here. Anybody have any questions about these? Okay, so let me start with this last point. And Robert, was you that mentioned the last point there about calculating the slope?
Yeah.
Yeah, okay.
Yes, so, that was.
So again, what? It was? Okay, so let's look at this for a second. Oops. I didn't want to do that to you. So when you have a a function, a graph of a function. Okay. Y equals f of x. And you've got a point in the domain, so that gives you an ordered pair on the graph. And when you want to know what the tangent line is at that point, so I'm going to sketch it. Okay, so I just sketched the tangent line. When you want to know what that tangent line is, the way we express that knowledge is by finding a symbolic representation of it. Okay, that is, we find a formula for it. And so we all know that the formula for a line, the point slope form for a line, looks like this. And the y naught and the x naught, right, are kind of given to us already because we know what point the tangent line is touching on the line, on the graph of the function. But what I want to impress on you is the fact that we don't know the slope. That's not obvious to us. Okay. So let me copy this to the next page and I'll keep talking about it. Now, if we want to, quote unquote, know the line and find a symbolic expression for that line, there's two things we can do. Okay, because slope is the only thing that's missing from that equation. So there's two ways we can find it. So the first way is if we have a graphical representation, we can use the scales on the axes to estimate, oops, not estimate, estimate the slope equals the rise over the run, okay, which we will denote as delta y over delta x. Okay. So if you have a graphical representation of your function and a graphical sketch or graphical representation of your tangent line, like we have here at the top of this, the top right of the page, top left of the page, then you can approach it in method one here, I've written here. So I'm not going to put tick marks and scales on both axes, but what I will do is, let's see, what I'll use purple. If you use the tick marks on the axes, you can pick another point on the graph. And I'm denoting this in purple. And then with that other point and using the axes, you can calculate or estimate, and this would always just be an estimation because you're doing it visually. You're not using a formula or anything. You can estimate delta y over delta x, right? And then you say your m is approximately equal to delta y over delta x. Then finish the formula. For the tangent line. Okay, so that's one way you can do it. And I demonstrated how to do that last time. Finding or estimating the slope of a tangent line from a graphical representation. The other approach, the second way to find the slope, is if you have a symbolic representation of the function f of x. Okay. this becomes, well, then we use the concept of secant lines that I talked about last time. Okay, so here's the idea. And I'm going to use a graphical representation of what's happening, and then I'll change that into a symbolic approach that I'm trying to make sure you understand or appreciate. So here's the graph of our function. There's the point. There's the value at the point. Here's my sketch of the tangent line. So what we're going to do is, since we have a formula for the function, I'm going to find another point on my graph. So let's call this D. And so up here we get f of D. And then these 2 points determine a line, and it's that line that I'm going to find the slope of. Okay, so this is called a secant line. And so I'm going to say my slope is approximately equal to the slope of the secant line. So I'm going to say f of D minus f of C, because that's delta y, over D minus C, because that's delta x. So here I'm using the formula, the symbolic representation for f of x, to find, actually to estimate m. So those are the 2 approaches we have to estimate m. One if we've got a graphical representation, one if we've got a symbolic representation. There's no real way to do this if we've got only a verbal representation of our function. If we have a numerical representation of a function, basically you use method 2, okay, with the values that you have. If you've got a numerical representation of the function, you're really limited limited to these other numbers you can plug in. If you've got a symbolic representation, you can plug in whatever you want for D. Okay. So let's do an example of the second approach. So let's find the equation of the line tangent to y equals 2x minus x squared at x equals 1. Okay, using the second method. So we'll do some scratch work here. So that means I'm starting scratch work. This isn't anything that you'd ever turn in, but it's stuff that you could probably reorganize into a solution. So our tangent line goes through the point, and it's the 1 comma, in this case, f of 1. So what's f of 1? F of 1 is 2 times 1 minus 1 squared. That's 2 minus 1. It's 1. So our tangent line goes through 1 comma 1. Okay, so that's 1 point that's on our tangent line. Now I need to find another point that's on the tangent line, but that's not going to work. So I'm going to find another point that's on the graph of my function that's nearby. And so let's choose x equals 2. Okay, it's a little bit bigger than 1. It's above 1. So what point is on my graph? But when x is 2, it's 2 comma f of 2. So that's 2 comma, or 2 comma 2 times 2 minus 2 squared. Well, 2 times 2 is 2 squared. And so that's 2 comma 0. So that's my second point. So it's these are the 2 points I'm going to use to calculate my slope. And so the slope is the difference in the y values, 1 minus 0, over the difference in the x values, 1 minus 2. And so that's 1 over negative 1. So the slope is minus 1. Okay, so what this tells me here, so here's my answer. Slope of my tangent line is approximately m equals negative 1. Okay, according to this calculation. But if we go back and look at the picture, so if we look at this picture, this distance here, well, if I were to make it smaller, if I were to bring d closer, that would bring this point down closer to my point of tangency, and the slope of the line that I get might be a little bit better. So let me draw this picture a little bit bigger. Just to make a point. So if I have a tangent line like that, and if let's use purple, if I use this point to approximate the slope of my tangent line, this is a secant line. So let me call this slope m sub sec for the slope of the secant. And let's call the slope here m tangent. And the idea is that the slope of the tangent is going to be approximately equal to the slope of the secant. But in an approximation, there's always error. And in life, we want error to be small. Okay. So in my picture here, let's use green. If I move this point down the curve and say I move it to here, so the purple input becomes this input there, right? Then the slope of my secant line is closer. The slope of my green secant line is closer in value to the slope of my tangent line than the purple line was. Okay. So the idea here is closer is better. So in the example I did over here, I picked x equals 2 to calculate my secant line, but wouldn't it be better if I used x equals 1.1? Because 1.1 is closer to 1, right? That's closer to the place I'm calculating the tangent line. So let's calculate that slope together. So what's the slope of the secant line if I'm going from 1 to 1.1? Okay, the slope of that secant line is f of 1.1 minus f of 1 over 1.1 minus 1. All right, so we know f of 1 is 1, right? Yeah. So what's f of 1.1? It's 1.1 or 1.1 times 2 minus 1.1. And then downstairs I have 0.1. So 2 minus 1.1 is 0.09. So I've got 1.1 times 0.9. And 1.1 times 0.9, I think it's 0.99. And 0.99 minus 1 is 0.01. And so 0.01 divided by 0.1 That's 0.1. All right, so this tells us that the slope of our tangent line that we're looking for is approximately equal to 0.1.
Shouldn't it be negative?
Oh, yeah, thanks. From this step right here? Yeah.
Yeah,
good
like
catch.
the third to the last.
Yeah.
Okay.
Yep, good catch. Thanks, man. Okay, well, then a person can say, if starting at 2 and 2 is far away, and so that we chose 1.1, can't we say 1.1 is far away from 1 and choose something that's smaller? And the answer is yes. Okay. Because if I use 1.01, that's going to be closer to x equals 1. And so the error in the secant line slope should be smaller, right? The secant line slope should be closer to the tangent line slope. And this is true. And what that leads us to do is this. Ugh. I'm going to show you a table of values here for the slope of the secant. And the inputs, I'm going to have 1 plus a delta x. Okay, so the first delta x was 1. The second delta x was 0.1. So these are going to be my inputs for my second coordinate on the graph. And if I use these to calculate the slope of the secant, well, we saw the first calculation we did, we got a slope of -1. The calculation we did here on the left side of the page, we got a negative 0.1. And if you go and do the work, you'll see you get a negative 0.01 and a negative 0.001 for those other inputs. So what we're doing here, what this table is kind of telling us, or it's suggesting that the limit as our delta x goes to 0 from below of the secant line looks like it's equal to 0. And then if we do the same thing from the other direction, that is, make a table of values for the secant, the slope of the secant line. So here will be our new input values. Here will be our calculated secant values. Let's see, we'll start at 0, and then we'll go up to 0.9, and then 0.99, and then 0.999. So these are all getting closer to 1 from below. You can do the calculations and verify that the secant line, the first secant line, has slope 1. And then I get a secant line of slope 0.1, and then 0.01, and then 0.001. And so these numbers make it look like the limit as delta x goes to 0 from above of my slopes is 0. So putting these two things together, that suggests that the limit as delta x goes to 0 of the slope of my secant line is actually equal to the slope of my tangent line. Oh, I should say, no, that's not what I want to do. I want to do this. It's 0. So in fact, if you take the formula for the function, and we're interested in x equals 1, and you graphed it, you get a downward opening parabola where the vertex is at 1. And if you were to sketch the tangent line, you'd say, oh, it looks like that tangent line is horizontal, and horizontal lines have slope 0. Okay. So the picture would bear out this idea that the slope of our tangent line should be 0. And what we had been doing is we had been calculating slopes of tangent lines through, or slopes of secant lines through points that approached that. Okay, so there's a principle here. If f of x is nice at x equals c, then the slope of the tangent line equals the limit as delta x goes to 0 of the slope of the secant line. You can always do this. Okay, and using the formula for the slope of the secant line, oh, I don't have room here. I need to move this over. Using the formula for the slope of the secant line, or slope of the secant line, you get this. So this gives us a formula to calculate the slope of a tangent line whenever we want to. All you need is a formula for f and an input for where you want to calculate. So let's do this one more time with this example.
I have a really quick question,
Yeah.
actually.
Huh?
So, could we also use the rules for derivatives? Because that's what I had used, and I had gotten y equals 1. That was the same line that you got for the tangent line.
Yeah, okay, so let me get back to that, Robert. Okay, good
All right.
question. Make sure I answer that question before we end today, and we've got 9 more minutes. So the slope of the tangent line is supposed to be the limit as x goes to 0, in this case of f of 1 plus x minus f of 1 over delta x, f of 1 plus delta x. So let's use the formula for f. And so this means I get 1 plus delta x times 2 minus 1 plus delta x. And f of 1 is 1. Okay, so just playing for a second, what if I wanted to do the naive evaluation here? Well, this would be 0 and this would be 0. And so I'd have 1. So my first term here would be 1. My second term would be 1. So 1 times 1 is 1. And so I get 1 minus 1. And so that gives me 0 in the numerator. And delta x is going to 0. So this is 0. So I get 0 over 0. Okay. So I can't do naive evaluation here. And how does that meme go? Narrator, you can never do naive evaluation for these. Okay. Naive evaluation will never work when you want to calculate these slopes of tangent lines. If it works, you did something wrong, right? You should always get 0 over 0. So let's keep working this out. I get the limit as delta x goes to 0 of 1 plus delta x. And then over here, this is 1 minus delta x. This is over delta x. Oh, there's a minus 1 here too. So multiplying the top out, you should just probably see that that is 1 minus delta x squared minus 1. And then these ones cancel. So I've got minus 1 over the quantity delta x squared over delta x. And so here's where a beautiful thing happens. The delta x that's downstairs cancels with one of the delta x's that's upstairs. And now you can do naive evaluation. Now it'll work fine. So you get 0 in this limit. And even if you do it by hand, you'll get 0. You'll see you get 0. Okay. So this calculation here agrees with what our two tables, what our two tables were suggesting here. This idea that the slopes of the secant lines get closer and closer to what we're calling here the slope of our tangent line. So back on the previous page, the thing that I put in the red box here, this is how you calculate the slope of a secant line when you have a slope of a tangent line when you have a formula. And what you need to recognize and remember is that this quotient right here is the slope of a secant line. And maybe I'll just rewrite this down here. M tangent equals the limit as delta x goes to 0. This quotient here is often called the difference quotient. Oops. Because it's delta y over delta x, and each of those deltas is a difference. Okay. So the slope of the tangent line is the limit of a difference quotient. Okay, the limit of the slope of the secant lines. So Robert, you said that you asked the question, why can we just use the derivative formulas? So you revealed your hand in a way. You revealed that you know that there are these formulas, and we're going to explain to everybody who hasn't seen these formulas before what you're talking about. And yes, eventually you'll be able to use the formulas that you're talking about, Robert, but not right now. Right now, I want to make sure that everybody knows where those formulas are coming from, because what we're going to do, this notation is cumbersome. This m sub tangent and m sub secant or sub sec, it's not standard, it's cumbersome, it doesn't have a lot of information, like it doesn't tell us what x equals c is. So what we're going to do is if I have a limit, if I'm looking for the slope of a tangent line of a point, slope of a tangent line at a point, I'm going to call this f prime because it has to do with f, and prime is just a little dingbat that I'm adding. And then I'm just going to put a c there to remind us that we're talking about the tangent line at x equals c. Okay, so f prime of c here means the slope of the tangent to the graph of y equals x, or y equals f of x at x equals c. Okay, and then next time, right, I think I'm at the point where I can say this. Next time, we'll see that if you're given a function, y equals f of x, the rule that takes an input x and assigns an output f prime of x is also a function. Called the derivative of f. Okay.
Could you repeat that last part?
Yeah, I'd be happy to, because it's a very important thing.
Thank you.
So next time we're going to explore this idea that if somebody gives you a function f of x, say it's the sine function, you can define a new rule that takes an input and as an output gives you this value f prime, that is, uses this limit definition and calculates a number f prime of x. So the rule that takes x to this value f prime of x, this is also a function. And it's a function that we call the derivative of f, that is the derivative of this function. Okay, so given a function, what this new derivative function takes x to the value of the slope of the tangent line of your original function. Okay, And this function is called the derivative of f. It feels complex right now, and it is kind of complex. As we work with it more, it'll become more natural. But you would do well to remember that this new idea of a derivative is just a tangent line. It's just a slope of a tangent line. Okay. So read the first couple sections of chapter 3. Maybe go read the first section of chapter 2. And we'll explore these ideas more deeply starting Monday. Eventually, there'll be rules for calculating f prime from f. But until we talk about those rules, this is what we're going to use. Okay, so it's going to require a little algebra, and then it's going to require us to evaluate a limit. All right? And the functions that we'll start with that we'll be most interested in calculating derivatives of are going to be monomials, simple polynomials. Okay. Ooh, what happened there? Any questions before we call it a day? Okay, I'm going to put a link to a screencast I made on calculating a derivative of the absolute value function. So once you've read the text and heard it talk about the derivative of the absolute value function, you can go watch the screencast. But watching that screencast and reading the text, that's all I really want you to do before Monday. You can work problems too, of course, always work problems. And if you've got questions or have problems taking learning target quizzes, don't hesitate to email me or text me, and I'll try to get those smoothed out as soon as I can. Like I said, I'm caught up with all the grading. I want to encourage you all to take these quizzes and make progress toward your final grade in the class. Work now, don't procrastinate. It's not going to work at the end of the semester to leave everything to do until then, because you will be tempted to cheat. You will cheat. It'll become obvious to me, and then everybody will cry. So do yourself a favor and take these learning quizzes now. Just start taking them now. They're totally low stakes. Each is about 3 or 4 questions. Just start racking up wins now, and we'll all be better for it. Okay, I'll leave it there. Have a good weekend. Stay cool. Let's hope the weather holds for everybody. We don't have more wildfires. I'll be thinking about y'all.
Professor, I have one question. I sent you a message in the private about the learning target quiz.
Yeah, so you asked, has a link been fixed?
Yes.
I'm still not sure what's causing your problem.